Okay, so we're going to talk about the intro to series, particularly Newton's method. So suppose we want to approximate the solution f of x equals 0. And also suppose we found an initial approximation to the solution. We're going to call that x0. So if x0 is some quick guess, not so good, we want to find a better approximation. We need to first find the tangent line to f of x at that point that we're guessing, right? That x0. So if you look at my graph here, this red line is going to be our function, okay? And then the green line is our tangent at x1, and then the blue line will be our tangent at x0. So remember that x0 is our first approximation, the not so good one, okay? So if this line's going to cross this blue line that we're looking at up here, it will cross the x-axis much closer to the actual solution to the equation than x0 does, okay? So let's call the point where the tangent line at x0 crosses the x-axis x1, okay? So now we're looking here, right? Where it crosses. And we're going to now use this point for our new approximation. Okay, so how do we solve this, right? We know the coordinate x1, which is our new one, our new approximation from that tangent line of our original guess, and we know as 0, right? Because we know that that lies on that tangent line. So let's go ahead and plug these points into from the tangent line above, and we're going to solve for x1. Okay, so if 0 equals f of x0 plus f prime of x0 times x1 minus x0, we can then say that x1 minus x0 is f of x0 over f prime of x0. Okay, therefore x1 is equal to x0 minus f of x0 all over f prime of x0. Okay, so now we're going to repeat to find an even better approximation. Okay, we need to we'll look at the tangent line to f of x at x, and we're going to use its root, which we'll then call that x2, as the new approximation to the actual solution. So doing this again is going to give us that x2 is equal to x1 minus f of x1 over f prime of x1. Okay? So we want to keep following this process, and we will begin to get a sequence of numbers that are actually getting very, very close to the actual solution. This is Newton's method, okay? So if x of n is an approximation of a solution of f of x equals 0, and f prime of x of n does not equal 0, then the next approximation is given by x of n plus 1 is equal to x of n minus f of x of n all over f prime of x of n, okay? So when do we stop? How many times do we do this process? When 2 or more successive approximations agree to a given number of decimal places, okay? And we'll see that in an example. We need to be solving, first of all, that f of x is equal to 0 in order for Newton's method to be applied, okay? The second fact is that we need to get our hands on an initial approximation. So we need x0 somehow. A common way is to sketch a graph, okay? So we can get an estimate. But another way is that if we know there's a solution to a function, then we can use the midpoint, okay? So let's do this example. Using Newton's method to determine an approximation to the solution to cosine x equals x that lies on the interval of 0 to 2. So in this example, we weren't given an initial guess, but we were given an interval. So at that point, we can use the midpoint between 0 and 2, which we find to be 1, to be our x0. Okay? So we must have a function in our form of f of x equals 0. So we need to rewrite that cosine x minus x equals 0. Okay? And then again, the general formula for Newton's method is that x of x and plus 1 equals x of n minus f of x of n divided by f prime of x of n, right? The first derivative. So then we're going to plug in some things. So we're going to plug in cosine of x of n minus x of n right? Because that's what it is, cosine minus x equals 0, right? And then we'll do negative sine x of n minus 1, right? Because that's the derivative, okay, of this formula here, the derivative. We're focusing strictly here. Okay, now we need to obtain the first approximation. So for x of 1, we're going to take in the midpoint, which we determined to be 1, right? And we're going to say that x of 1 is equal to 1 minus cosine of 1 minus 1 over negative sine of 1 minus 1. And that's going to give us this decimal. Okay, and this is our x of 1. Okay, so then we'll repeat the process again to find x2. So we'll take in the value that we found for x1, which was 0.75, this long decimal, and we're going to subtract that from cosine of it, minus it, over negative sine of that x1 minus 1. Okay? And then we get this value. And again, repeat. Here is where I want you to try the calculation, okay? If we're trying to find this, right, then we're going to plug in x2 and follow the same exact formula here for whatever n we're on, okay? And then you should find these to be your values, proceeding that you do the work correctly. Okay, key takeaway here is when to stop. If you look at the last 6 decimal places, you'll know that they vary only by their last values. Okay, everything else is exactly the same. So you could stop at the 4th. Okay. Second example, say we want to use x of 0 equals 1 to find the approximation to the solution. The cubed root of x is equal to 0. So this might be a silly example because clearly we know that x equals 0, right? But let's just take a look. If we have Newton's formula, x of n plus 1 equals x of n minus, and then we go ahead and take a look at this, okay, and plug that in, we'll get x of n to the 1/3 over 1/3 x of n to the negative 2/3 is equal to x of n minus 3x of n, which gives us negative 2x of n. Okay, so really no computations are needed here. As we look, they're going to get further and further away from the solution that x equals 0. So for our first value, we would get negative 2. For x of 2, we get that to be 4. For x of 3, we get negative 8. And for x of 4, we get 16. Okay, so the takeaway here is understanding what Newton's method provides for us, but also what we need in order to do and use Newton's method. Okay? Practice that problem on the first example we did, trying to validate that my x3 and my x4 values are the same as the values that you get.